so very exciting to have Jose speaking, and he's going to be telling us about some Schelling orders are better than others. So, please.
Okay, thank you. Thank you very much, Liam, and thank you very much to all the organizers. It's a big honor to be speaking here and to be sharing my math with so many wonderful people. So yeah, I'm going to talk about the fact that some Schelling orders are better than others, and I'll try to explain what that means. I do not expect you to understand the title and or what it could potentially mean. And I okay. Good. And so let me just start by saying that everything that I mentioned is joint work with Alex Heaton. And we posted a paper recently on the archive if you want to check any of the things that I talk about right now. And so let me start by giving an idea of what I'm going to be talking about. And so in this setting, and I'll talk about a little bit more about simplicial complex in a second. But the idea is that I'm going to study, or I want to study Schelling orders. And for this setting, to study this, what I want to be thinking of is either a pure polytope or a simplicial complex, and polytopes are going to play an important role in the end of the talk. So just keep in mind that polytopes can be showing up, even though I'm not going to make the formal definitions for them. And a Schelling order, the way how I like to think of the Schelling order is I'm going to construct K by adding one facet at a time. I can imagine of my complex being built some sort of as a Lego. And what I want is that in each step, every time I add something new, I have control of what I'm putting in, okay? And one of the reasons, or there's many different reasons to like Schelling orders, and I'll go into details in a second, but they allow us to compute many interesting things about a simplicial complex or a polytopic complex. So for example, we can keep track of topological invariants like the homotopy type, or if you want something simpler, an Euler characteristic, every time we add our new a new piece to the puzzle. Or we can use this to compute and understand combinatorial invariants. For example, if you know what the Somerville equations are, there's a very beautiful proof using shellability. And you can compute algebraic invariants, so Hilbert series of Stanley-Reisner rings, or you can use it to check the simplicial complexes con Macaulay if you like commutative algebra. And consequently, there has been a significant amount of work in trying to, so if you give me, or in trying to answer the question of whether a simplicial complex or a polytopic complex is shellable. However, here's a very vague question, something that has been less studied, and which is what the point that I want to make right now. So, which is that is it enough? If you give me a simplicial complex or a polytopic complex, is it enough to know that it's shellable, or do I get some advantage from shelling an order from shelling a complex in a different way? So there's many different complexes that have many different Schelling orders, and it might be beneficial to choose one for our needs. And I want to explore this idea. And so let me just start by giving you a little bit of an intuition. So I'm going to be talking about pure simplicial complexes, which are set systems that are closed under inclusion. And before I tell you what shellability means, let me just give you two quick examples. There's the complex on the left. Can you see my pointer?
Yes.
There's the complex on the left, which is a shellable simplicial complex. And there's a few different ways to construct it inductively. I want to add one triangle at a time, and I'll develop this example a little bit more in the future. But it's probably more instructive to see the one on the right, in which it's not going to be shellable. And what's really strange here is gluing this triangle here on the right. And when I give you the definition, if you're bored and you want to check something and you don't know what shellable means, you can try to check that this complex on the right is not shellable. And the issue is going to be given by these two vertices over here. And so now that you more or less have an idea of what I want to do, which is construct these simplicial complexes by adding one triangle at a time or a simplex at a time, let me give you the definition. So for a pure simplicial complex, I'm going to say that it's I would say that this pure simplicial complex is shellable if there is an ordering of the facets or the faces of maximal dimension, f1 up to fk, such that if I look at the, so I can look at the new faces in when I attach the facet or the face fj to the faces f1 up to fj minus 1, and I can look at this. So each of these simplices can be thought of as a Boolean interval, and the new things that I'm attaching is again a Boolean interval. That means that's the same as saying there's a unique minimal subset of fj that is not contained in anything in any of the previous faces. So among all the subsets of fj that are not contained in the previous one, there's a unique minimal one that is not contained. And so such an order is called a Schelling order, and the special subset fj are that is the minimal new phase, so to say, is called the restriction set of the Schelling order. So I have this ordering, I have this way to construct it, and now I have some combinatorial invariant or some invariant of the phase that I can use to keep track of the way how I'm gluing my simplicial complex. And so let's go back to the very simple example of what I'm talking about. I have my complex on the left, and I labeled the faces, the triangles, by 1, 2, 3. And what I want to do is I want to start constructing this complex by adding 1, which is the phase that contains vertices A, B, C. And I can look at what's the minimal new phase that is attached. It's just the empty set. And so here I have the whole phase poset of this guy. And what I'm doing is, well, I attach the triangle ABC. There's a unique minimal thing, which is the empty set. I then proceed to attach 2, and I can ask, well, what are the new faces that I attached when I include B, C, D into my complex? And it turns out to be everything that contains the vertex D. So it's again a Boolean interval. And again, I can keep going, and I look at 3, and the new faces are anything that contains E. You can check quite easily, again, a Boolean interval. So that's a Schelling order of my original complex. And the idea is, well, we can ask, if I give you a simplicial complex, what kind of properties can I learn if I know that I have a Schelling order? So it's kind of easy to look up many examples that are not shellable, but if I have one, there are lots of interesting invariants that I can compute. So for example, I can look at the H vector. If you've seen this from H vector theory, it's a transformation of the phase numbers, or the counting the number of simplices in each dimension, but you can also define it in terms of the Schellings. And what you do is, well, remember that every time that you attach something, you have these lower intervals in the Boolean poset, and I just keep track of the sizes. So Hj is the number of facets such that the restriction set has size j. And these numbers here have lots of meaning. For example, Hd, the largest, so if my complex is d minus 1 dimensional, I can look at Hd, and with that Hd, I can completely read the homotopy type of my simplicial complex, or as a topological space. I can prove Kohn-Macauliness, or I can compute Hilbert series of Stanley-Reisner rings. And there's all sorts of techniques in order to compute this combinatorially when you have a nice Schelling order. And so the literature on this is actually vast. And on what is a little bit less interesting or vast, and perhaps a little less studied, is that we could actually think of these restriction sets and this partition of the phase poset combinatorially. So I could, for example, think of this collection of sets and imagine them as a, let's call this a set system, a family of subsets of a given set of the vertex set of my simplicial complex. And I can, for example, look at this as a poset or as a hypergraph. Now it's becoming trendy to talk about hypergraphs. And the thing is that for general simplicial complexes, these qualitative aspects of a Schelling order are way less studied. And what I want to make the point is that it might be worth taking a look at them. So here's an example of what I mean. In the complex that I showed you before, here's a very different Schelling or a different Schelling order, which is just 1, 2, and 3. And if you look at the partition of the phase poset here, these two are different. And the point that I want to make is that perhaps by looking at the compositions, I can learn something more, and by choosing my Schelling order wisely, I can perhaps solve some problems better. So that's basically what I want to do. And in order to address this issue of many different complexes, what I'm going to do is I'm going to talk about a complex or a class of complexes that has many, many different Schelling orders. So instead of developing techniques to have a Schelling order, I want to, if I know that I have many, many Schelling orders, what can I say about the combinatorics and the difference between the combinatorial structure of such decomposition? So let me define matroids, which are basically or if you've ever met me, you probably know that I love working with matroids. And I'm going to define them a la Bjorner. So maybe many of you know that there's a bijection between the number of people who write papers about matroids and the number of definitions of matroids. So here's one. Then I'm going to say that a matroid is a pair E, comma I, and this is the independent sets that people usually talk about, where I is a simplicial complex. And then I'm going to do a small trick, which is that for every order of the ground set of the matroid, I can look at the bases or the maximal phases, and I can order them lexicographically. And I'm going to say that this pair is a matroid if and only if, for all these orders, what I get is a Schelling order. So in a sense, this is equivalent to this is the same data as a matroid. And what this is saying is that a matroid immediately comes equipped with at least E factorial Schelling orders. So many, many of them. And what I want to do is exploit it. So let me just give a very simple example of the kind of properties that bias something like this. So here's a graphical matroid. For those of you who don't know, what you do is you look at any graph, and then you declare, so the ground set is the set of edges, and you declare them to be independent if they contain no cycle. So in other words, the maximal or the facets of my complex, or which are oftentimes called the bases, are the spanning trees of this graph. And what I have done is, for the sake of simplicity, I labeled all these numbers here, which I want to think of as a linear order. And I ordered my spanning trees here. You can check that these are all of them. I ordered them lexicographically. And then for each of these spanning sets, I can check what are the new faces that I am attaching. So let me say, for example, what are the subsets of 1, 3, 4 that are not contained in 1, 2, 4 or 1, 2, 5? Well, I could easily see that 4 is contained in a phase before, 1 is contained in a phase before, but 3 is not. So 3 has to be the restriction set. If you believe me that ordering these things lexicographically is a Schelling order, or here with 2, 3, 4, I can check that 2, 3, and 4 already appeared all in one of these phases over here. But if I check at 2, if I look at 2, 3, it did not show in any of the triples before. So you play this game. It's not. I mean, it takes a little while, but you can compute, and then the H vector or the invariant that I like to keep track of is I look at the sizes of these purple sets, and they are so we get 1, 2, 3, 2, and so I know that this matroid as a simplicial complex, for example, is the wedge or is homotopy equivalent to the wedge of 2 spheres, and there's different things that I can do. And in particular, another thing that
Diodorus has a question. He's asking, are these Schelling orders reversible?
Yes, and it will come soon. I will. So my main theorem, for example, implies it. I mean, it's a theorem of Chari from '97 that this one is reversible. But you will see in a second why this is reversible from or an argument that I like a lot. But you can also order these.
Sorry, one more question. So Federico Ardila is asking, is this poset one of Laverna's posets on bases?
It's the internal poset of the bases, yes. It's the exact same one. It's the in poset of Las Bernias. So, and that's kind of where I'm going. This has a lot of structure, right? So what I want to do is I want to order these guys by inclusion, and this has a lot of structure. But the point is, well, here I gave you an ordering of these bases here, of these edges here, and if I change the order, I can change this poset drastically. So and that's kind of where I'm going. So let me motivate. This is one of my favorite conjectures that I've been trying to think for a long time. It's a conjecture of Stanley that is old, from the Cohen-Macaulay paper in 1977, which says it posits that the H vector of the independence complex of a matroid is a pure sequence, meaning that there's a collection of monomials closed under divisibility such that there are exactly Hi monomials of degree I, and such that all the maximal monomials have the same degree. I'm going to give you the solution for the previous matroid here. What can you do? You can look at this partially ordered set here and hope, cross your fingers and hope that this is actually the poset of a is a poset of monomials ordered by divisibility. And if you play with this one, you see that and I chose it so that it happens. It turns out that this poset over here is the divisibility poset of a monomial, and this has the correct H vector, because you can see that the grading here is given by the size of the internally passive, or by the size of the restriction set. So in this case, it solves the conjecture, but it turns out that there's something special going on, because here I have the exact same, the matrix of the exact same graph, but I decided to choose the order in a different way. So before I had 1, 2, 3 on this left triangle over here, and now I have 1, 2, 3 to be a spanning tree. And then when I compute the same poset, or the analogous poset, I get something that is clearly not isomorphic. And when I try to play the game of adding the monomials here, I cannot do that. So in a sense, or what I want you to take out of this is that by choosing a different Schelling order for my given problem, I can, so there are ways in which a Schelling order can be better than other for a specific goal. Okay, and what we're proposing is, well, we should study this carefully. I do not want to start listing all the theorems that are known about Stanley's conjecture, because my talk would be over basically. But the point is that there's several results that are already known in the literature. For example, Aaron Dahl proved that there's many different ordered matroids for which this works. He called them internally passive matroids. The restriction sets of this poset is very similar to a divisibility poset, and this is very related to what Federico asked a few minutes ago. There are structural results on what you get when you shell with these lexicographic orders. For example, there's results by Dawson showing that this is a gridoid, and this was just, recently generalized by Brian Gillespie, not for bases but for more general poset. And then there's the result. So there's a few results by Las Bernias that are quite beautiful and tell us that this thing is highly structured. And then another thing that you can do is, well, you go through matrix, through many different matrices, and you look at these restriction set posets, and usually you can like squint, or you can look at it and change a few of the containment relations and prove Stanley's conjecture by hand. So if I look at my poset here, I could decide that I change a few of the relations in the poset, and I could try to construct the shellability, the multi-complex. And so what I want to do is I want to propose a theorem in order to attack this. And I'm going to use it, or I'm going to do it by infusing some polytopes and some discrete geometry. And in fact, one of the nice things about it is that it opens a lot of questions that I find really interesting. So let me just briefly tell you what this is. So given any matroid, we can construct a matroid polytope. This is standard. What you use, you look at the characteristic vectors of the bases. Don't worry too much if you don't know exactly what that is. And then there is a dual matroid polytope, which it doesn't really matter which geometric realization you choose, but there's a dual polytope, and the important thing is that the facets of this polytope are in correspondence with the basis of M, or the facets of the independence complex. So there's this very, very nice bijection. And it turns out, I have not defined it yet, but any polytope is shellable. So this is you can read chapter 8 of Ziegler's book, and there's a very beautiful introduction to shellability of polytopes, which are a little bit more complicated than just simplicial complexes. But there's a very beautiful argument. The first proof of shellability is this idea of a rocket shelling or a line shelling by Bruguière and Mani, which in a sense, or in a dual setting, it tells you, well, if I want to shell my polytope PM star, all I have to do is is order the vertices of PM according to a linear functional, and my vertices correspond to facets, and that order is going to shell my simplicial my polytope. Okay, so this is classical, and it's kind of well known. I mean, I'm just specializing to the case of matroid polytopes. And remember, facets of this guy are the same as facets of the independence complex. So let me just tell you the theorem, which is rather interesting, which is that if I look at any shelling order of PM star, well, that's an ordering on the, I can interpret this as an ordering of the basis of the independence complex. And it turns out that it's also a shelling order of I. So I have shelling order of my polytope, and then I have a shelling order, it induces a shelling order of I. And even more, if I look at the line shellings and the classical way how you shell polytopes, what you recover is exactly the internal activity. So if you know about this, the normal fan of the matroid polytope is refined by the braid fan, or the chambers of the braid arrangement. And it turns out that a generic linear functional corresponds to a permutation, and the internal activity turns out to be an invariant of the shelling coming from such a linear order. And just to give you an idea of what's going on, you know, or try to paint this idea in a way, this should be shocking. The first time that I saw this property, I had a hard time parsing it. The point being that on one side you have PM star, this is a polytope, and in a sense this has easy geometry and topology, something that we understand really well. On the other hand, it has complicated pieces, because this is not a simplicial polytope, this is not a simple polytope. Our matroid polytopes are in general complicated. So it's something that is simple topologically, but each of my pieces in my puzzle are complicated. So if I look, for example, at a simple matroid, the uniform matroid on 4 elements of rank 2, I can compute that the dual polytope turns out to be combinatorially equivalent to a cube. On the other hand, if I look at the independence complex, I can have hard geometry or topology. It can be a wedge of many, many different spheres, and it's homotopy equivalent, but the homeomorphism type is not so easy to handle. On the other hand, what we gain when we pass to the independence set is we have easy pieces. All of my phases are simplices. And what I'm saying is that I can use the geometry on the left-hand side in order to infer topological combinatorics statements on the right-hand side. In particular, all the internal activity theory that we like, for example, in order to compute things from the Todd polynomial, for instance, can be inferred this way. So
Jose, just yeah, maybe try and wrap up in
you want 5 minutes or no?
No, I have 2 minutes. Sorry, I forgot to give you a
Okay.
warning because I was listening. So yeah.
Okay. So let me just go very, very quickly. So the idea is we would like to use this machinery of polytopes. And the idea is that if we look at line shellings or linear functionals, that's not enough, but that's a translation of the theorem of Dahl. In any case, if we want to tackle Stanley's conjecture, we can try to play the following game. You can think of this shelling as taking the polytope and sweeping it with a hyperplane. What happens if I start wiggling in the middle of the process with a different hyperplane and change the order along the way? And it turns out that we did a lot of computer experiments with this, and it turns out that it looks quite promising. So you can download some code and play with it later. I put up a GitHub webpage where you can download it. But the point is that when we start playing with this, what happens is that we get many new different restrictions set posets and many shelling orders that often behave like internal activity, very similar properties to the nice structure from Las Vegas and Dawson. And if we focus on special kinds of wiggles that I'm not going to get into the details here, many complexes or many matrices for which Stanley's conjecture cannot be proved using line shellings or the usual techniques follow by playing these wiggling techniques. And the point is that the results of cutting, so what we're doing is some sort of cutting and pasting of these internally passive posets. So I was going to say something about a few open problems if you're, or directions that we can take these two. But let me just finish. And if there are questions or more interest, I'm happy to answer questions.
Okay, first let's thank Jose for the whole talk. And yeah, there's some questions popping up in the chat. First, it seems like many people agree that it's a really awesome theorem. I also think so too. But yeah, so I think the first question that I didn't get to yet was from Theodoros, who said, what does the external activity tell you? You mentioned about the internal activity.
So the external activity, let me just say that this is one problem that I want to think about. The external activity you can think of as sweeping in the dual polytope. So you can technically also read the external activity by playing this game. What I still do not know is how you can combine them. But I think that it's a pretty similar game. So you have to change a little bit the story, but yeah, you can so you can think of both of them as dual. What you're doing then is changing 0 1s in the polytope, and you can still sweep and get the whole story together.
Thanks. And the next question is from Alexander Carman-Wu, who says, are the wiggles that don't come from perturbations of the polytope? Are there wiggles that don't come from perturbations of the polytope?
I'm not perturbing the polytope at all. What I'm perturbing is the linear functional that I use to sweep it, right? So here's let me just explain this picture a little bit better. I could take a linear order or a wiggling. Imagine that this is a matroid polytope, and I can order the vertices of this guy, which are the facets of the dual polytope, by ordering according to which one is closer to the red line. So I start sweeping, and then at some point I got bored of sweeping with the red line, and I decided, okay, I'm going to change for the purple line. And then you see that if I had continued sweeping with the red one, I would have 4, 5, and 6. But when I change, I get a different order. I swap the order of 5 and 6, and so I'm not wiggling the polytope, I'm wiggling the line. And so
sure, but of course, you know, wiggling the line is sometimes equivalent to wiggling the polytope, right? Or wiggling part of the polytope. So
I guess, but if you wiggle, you don't want to wiggle this polytope because it's not simplicial, right? So you want to preserve.
Okay, got it.
Cool. So the next question is from Sam Hopkins, who asks, is there a connection to the Tut polynomial for generalized permutahedra studied by Kalman, Posnikov, etc.?
So this is actually one of the questions that we left in the paper. We're actually, so this is new, or some of this is new stuff. I believe that there might be, you know, I think that we can read the Tut polynomial geometrically from this. But to be honest, I do not know much. I was wondering if, and this is also related to the question of Theodoros. You can actually read internal external activity simultaneously with a line shelling, and that's nice. But I do not know what happens when you start wiggling. So I know that there's probably something interesting going on, and I suspect that discrete geometry will play an interesting role, but I'm not entirely sure of what are the things that could potentially happen. So, by the way, the paper has a long collection of questions. Yeah.
Great. And then the last question, real quick, I guess, could be from Bruno, who says, for the wiggling, what happens if instead of a line shelling, you shell along a generic curve, assuming that you see all facets this way, like a drunken satellite instead of a rocket?
So that's pretty much, I think that's kind of similar to what we're doing here, except that what we want to do is, so I do not want to go back with facets, because that is, or that can be problematic. In fact, one of the things that our experiments show is that not even all the broken line shellings will work that nicely. So in a sense, you have to focus a little bit more on the kind of wiggling that you allow by playing with the normal fan of the polytope in order to have pleasant properties, because otherwise you can have posits that actually are completely crazy. But I guess that the whole point of the story is that when you know how to wiggle, you still get a lot of structure that we don't fully understand. And so if you look at our paper, it's packed with problems that I think are really nice. This is just a very nice connection that we discovered, and
Great. Yeah. So thank you again, Jose. That was a really wonderful talk.